On the 6th of August 1967, Jocelyn Bell, a 24-year-old PhD student, was working at a radio telescope observatory when she noticed an unknown signal from a certain point in the sky in her readings. Normally, this wouldn't have meant anything, but she had a funny feeling that she had seen this before. Intrigued by this, she checked old records of the same place. Sometimes nothing showed up, but in other readings there was a signal. This was strange, as stars don't just turn on and off. She pointed a telescope with faster readings at that point and waited. Months went by, but on the 28th of November of that same year, the signal reappeared. A clear radio signal was pulsing with an astonishingly consistent frequency of around 1 1/3 seconds. Confirming her findings with another telescope, the first pulsar was discovered. A pulsar is a type of neutron star, which is a strange remnant of a dead star. Although neutron stars are much smaller than even the smallest of main sequence stars, their properties push the limits of what is possible. Stars in the middle of their lifetime are on the main sequence, and they obtain their energy through fusion cycles like the proton-proton chain and the CNO cycle, which fuse hydrogen fuel into helium byproducts. Near the end of a star's life, when most of its hydrogen is gone, the star cannot fuse enough to provide a pressure to counteract the immense gravity of the star, and it begins to collapse on itself. This compresses the helium in the star, and it heats up enough to begin fusing this helium. The fusion of helium continues until the star has run out of that, and the cycle of fusion and contraction of heavier elements ends when the star reaches iron, which is the highest atomic binding energy of any element. This means that when the star tries to fuse iron into heavier elements, more input energy is required to get past this binding energy to fuse iron atoms into heavier elements with less binding energy, which means the reaction does not occur naturally under normal circumstances. At this point, when the star collapses, instead of fusing iron, the fate of the star depends on its mass. If the star is relatively small, a planetary nebula occurs, and a white dwarf is left behind. If the star is above the Chandrasekhar limit, meaning it has more than around 8 times the mass of our Sun, something more interesting happens. As the star collapses, the gravity of the star begins crushing the atoms within the star together. This pressure is so great that subatomic particles, or electrons and protons, are forced together into a dense mass of neutrons. These neutrons are degenerate, which just means that they are so tightly packed that quantum effects begin to matter in order to create a pressure to counteract the compressive force of gravity. At the same time, 3 things happen. Firstly, matter falls onto the surface of this densely packed neutron layer, and a rebounding shockwave forms, ejecting the collapsing star layers. Secondly, as the temperature increases with collapsing layers, photons, or electromagnetic waves, are able to interact and destroy themselves, producing neutrinos in the process, which creates a high-pressure region, also ejecting matter outward. Lastly, while the core collapses, some outer layers are still fusing lighter elements. The rate of this fusion increases as the temperature and density increase, which also creates an outward pressure. These 3 factors result in a supernova, a highly energetic explosion of the star's outer layers. What's left on the inside, however, is even more exciting. If the mass of the collapsing star core exceeds the Oppenheimer-Volkoff limit of around 2 times the mass of our Sun, the pressure exerted by the layers of degenerate neutrons cannot hold out against the massive inward collapse, and the collapse continues into a black hole. However, if the collapsing core is less than 2 stellar masses, or the overall star was originally between around 8 and 25 stellar masses, the outward pressure exerted by the tightly packed subatomic soup of degenerate neutrons stops the star from collapsing any further, and a neutron star has been created. This newly formed neutron star exists at the limits of what is physically possible and is well beyond anything you could imagine. Humans aren't great at understanding large numbers, so I'll try to add a bit of context. For reference, the average density of the Sun is around 100 grams per cubic centimeter. Try to take a guess at what you think the neutron star density is. I don't think you're gonna get it. It's around 1 quadrillion grams per cubic centimeter. That means that to get to the same weight as 1 teaspoon of neutron star matter, you'd need to stack giraffes from the Earth to the Moon 61 times. Now, neutron stars aren't completely degenerate neutrons. Just like how the Earth has layers and stars have layers, neutron stars have layers. On a neutron star's crust, charged particles still exist. There is an electron degenerate layer on the surface and a layer of iron and other heavy elements below that. As you go deeper, a layer of nuclei with an excessive amount of neutrons forms as positively charged protons and negatively charged electrons begin to combine into neutrons. This layer becomes increasingly dense, and the subatomic particles are pushed to slip between each other at speeds approaching the speed of light. At the very center, regular subatomic particles cannot exist, and hyperons are formed, which are like neutrons and protons, but they involve a weird type of matter aptly named strange quarks. A bit of a side note, when I was a kid, I loved those things on playgrounds that spin around. You know, those things that you spin yourself around on and you pull your arms and legs to make yourself speed up until you can't hold on and you just get flung off. My friend and I actually tried doing that with our LEGO Robotics Teams robot once to to give it the time of its life, and we almost broke it right before competition, but that's a story for another time. You're probably wondering how this relates to pulsars. Well, trust me, there's a good reason. Density isn't the only extreme aspect of a neutron star. During a supernova, the collapsing core retains most of the star's angular momentum, which, as stated by the laws of physics, must be conserved. Just as our Lego robot sped up during its wild adventure on the playground, neutron stars rotate faster, as most of the angular momentum of a star is compressed from something around 10 to the 7th power kilometers in radius to an object with a radius of just 10 kilometers. For reference, we couldn't hold on to our spinning robot after bringing only my limbs in for a decrease in radius of maybe 2 feet, so hopefully that makes sense as to why neutron stars can spin at relativistic speeds near the speed of light. Similarly, stars are filled with positively and negatively charged particles, which create a dipole magnetic field around the star's center. When a star collapses, its magnetic flux is conserved, so drastically decreasing the radius increases the magnetic field by about 10 billion times. It's important to note that the magnetic field poles on the axis of rotation of the neutron stars do not necessarily have to point in the same directions, just as magnets on Earth don't point perfectly to the north pole of rotation. Finally, we can distinguish the cool and epic pulsars from the regular neutron stars. As Eleanor from The Good Place would say,
"Guess what, Cheaty?
I am basic.
You basic."
Yeah, I noticed.
So we're moving on to the more interesting ones. If the rotation and magnetic energies of a neutron star are large enough, they can create a pulsar. Around a pulsar, the intense magnetic and electric fields rotate extremely quickly, and on the surface where it's slightly less dense and protons and electrons can still exist, these charged particles are accelerated to relativistic speeds along the magnetic field lines through a force contributed to by magnetic and electric effects. Around the magnetic equator, charged particles move quickly along closed magnetic field lines, where they build up enough electrostatic charge to cancel the magnetic force. However, the extreme rotational velocity of neutron stars messes with this. Usually with a dipole, field lines near the magnetic poles extend farther out from the source. However, pulsars rotate so quickly that past a certain radius away from the rotational axis, any point on a magnetic field line would have to have an instantaneous tangential linear velocity faster than the speed of light to keep the same angular velocity as the pulsar. The speed of light is the fastest speed that information can travel, which means that the field lines outside of this radius, or out of what is known as the light cylinder, cannot close, as the field lines cannot catch up with the rotating pulsar. This prevents charged particles from building up enough charge to counteract the magnetic field force, as they do not follow closed magnetic field lines, and they are flung from the pulsar, similarly to my Lego robot 10 minutes before a competition. I was not very responsible back then. Going off on a tangent again, gravitational acceleration points inwards towards a massive object. When the International Space Station orbits the Earth, its gravitational acceleration always points inwards towards the Earth, but its tangential velocity brings it to the side fast enough that by the time it would have accelerated down to hit Earth, it has moved to the side of the Earth and it begins accelerating or falling in a different direction. In the same sense, a charged particle moving along a curved magnetic field line is accelerated in a direction perpendicular to that line. When a charge stands still, it produces an electric field that dies down the farther away from the charge you go. Also, a moving charge emits a magnetic field that also dies down, like you'll see in a physics class dealing with the Biot-Savart law and current running through a wire. But when a charge accelerates, it emits perpendicular or orthogonal magnetic and electric fields whose magnitude at every point is proportional to the component of the acceleration vector perpendicular to the radius vector from the charge. This means these fields are maximized when they are both mutually orthogonal to the acceleration vector. These fields do not die down as much, and since a combination of electric and magnetic fields is electromagnetic radiation, aka light, it shows that light is emitted in a plane orthogonal to the acceleration vector, which is itself orthogonal to the magnetic field line. This shows that the charges accelerating along an open magnetic field line near the magnetic poles of the pulsar create light in the plane tangential to the field lines. This is an overly simplified description of what is known as curvature radiation, which is likely the source of the radio jet emitting from pulsars. Whether curvature radiation occurs depends on the acceleration of the charged particle, and in pulsars, it typically occurs around 100 to 1000 kilometers away from the neutron star's center. At this point, the magnetic field lines point relatively close to directly out of the pulsar's magnetic poles. As the charged particles are accelerated to relativistic speeds, the curvature radiation actually takes a conical shape pointed in the direction of the particle's velocity, which is the same direction as the magnetic field lines. This is why we see pulsar emissions only from a cone out of the magnetic poles of pulsars. But this still doesn't explain why pulsars are so powerful in radio wavelengths. When high-energy photons or electromagnetic radiation are emitted through curvature radiation, they interact with the intense magnetic field and other lower-energy photons to create electron-positron pairs, which emit more high-energy photons. These new high-energy photons undergo the same process, and a cascading effect creates what is basically an avalanche of electrons and positrons, all of which emit radiation. Normally, this radiation would be proportional to the charge of the particles emitting it. However, these electrons give off coherent radiation, which is where the electromagnetic waves emitted from multiple particles all come out in synchronization, which causes the observed radiation to scale with the square of the charge of the particles instead. Coherence occurs at higher wavelengths here, so it follows that the radio outputs from the magnetic poles of pulsars are incredibly powerful. As Jocelyn Bell noticed when she discovered them, pulsar missions oriented at Earth arrive in very consistent periods. Since a pulsar's rotational axis is often different from its magnetic polar axis, pulsars sweep their emissions away in a circular pattern. This means that when a pulsar's emissions are oriented at Earth, they often arrive only once during every rotation of the pulsar. Since pulsars rotate so unbelievably quickly, these pulses can still arrive at over 700 times per second. These pulses can be used to get extremely accurate measurements of time. To do this, many factors must be taken into account. A pulsar's radio signal is subject to noise, so each pulse is slightly different, which must be considered. There is also a difference between observatory clocks and actual time, which must be added or subtracted at each pulse. A delay caused by radio signals passing through the interstellar medium in space is also a complicated variable. In order to make reasonable time measurements, the frame of reference of the entire solar system, or more specifically, at its barycenter, can be assumed to have a comparable velocity to that of the pulsar system. So, based on the direction of the pulsar relative to Earth, the Earth's orientation relative to the solar system's barycenter, and the estimated pulsar's position in its system, variables of the time it takes for light to cross the solar system and the pulsar system must be accounted for as well. As the pulsar may be moving toward or away from the solar system, Doppler effects must also be considered. And if the pulsar signal appears to pass by something with a lot of mass, such as another body within the pulsar system or in our solar system, the effects of warped spacetime due to gravity must be included as variables. Lastly, a reference time variable depending on each pulsar is incorporated. After accounting for all of these, pulsar clocks can tell time down to 1/100 quintillionth, or 10 to the negative 16th power of a second. This is insanely accurate. To show just how accurate this is, here's what we're going to do. I'm going to add a timer for 10 seconds on the screen, and I want you to close your eyes, and when I say go, count down from 10. When you reach 0, press pause and open your eyes to see how accurate you were. I'll play as well, so we'll see if you can beat me. And I'm pretty good, so how about some stakes? If you beat me, I'll give you $10. If I beat you, you have to like the video. Alright, ready? 3, 2, 1, go. Alright, how'd you do? Well, I forgot to mention, but I was allowing the use of pulsar clocks in our little competition. So here's what I got. Did you beat me? No? Well, maybe next time, but I guess that means you owe me a like. So I hope that after all this, you think pulsars are as interesting as I do. Pulsars eventually convert enough rotational kinetic energy into radiated energy called spin-down luminosity, and of around 10 to 100 million years, they slow down enough that particles are not accelerated quickly enough to allow for curvature radiation, at which point they turn back into normal, basic neutron stars. I enjoyed researching these fascinating star remnants, and I hope you learned a thing or two. Thanks for watching.